So I'm going to repeat what I just said again. So we have learned last time how to efficiently create larger arrays that we might need. So sometimes we can always type things in, but I will never willingly type in 1,000 things at a time. For that, I need something more efficient. And there is a number of commands that will help us do just that. So one that we introduced that basically spaces out evenly the points between two endpoints is linspace. Log space does the same, but it works with logarithms of the values. And then there's a range. So quickly, please test on your computer. What is the difference between these two? So if I have np.linspace, you can open up your Jupyter notebook. So what is the difference between these two? If you don't have a computer, please work with a friend nearby. Say hi, introduce yourself, and kindly look over somebody's shoulder. So how many points do I have in array X if I use linspace? 5. So basically, and what is their range? So they start at 0 and the 10, and they appear equally spaced, and there's a total of 5 of them. So you basically request it. You can request 5, 500, 5,000, 5 million. Okay? Just don't print 5 million on your screen. You might sit there waiting. Okay? And a range, what does it do? How many points are there? 10. And what are they?
0 to 9.
0 to 9. So peculiar part of Python is that if it's right at the endpoint, it doesn't include it. So you would have to modify this to 10.1 to actually include a 10. And they're all equally spaced by 1. So those are two versions. Which one you prefer is the one you use. Okay? There is all possible mathematical functions you could think of. If you can think of it that it's a common mathematical function, it is there, look for it. Basic search always works when you type it into your favorite search engine. But sine, cosine, tangent, so they have sort of familiar shortcuts. The way we would use them is np.sine, np.cosine, and so forth. And square root is the one that we commonly use, is sqrt. Okay? So now let's start using these. So we can't even start working with numerical methods without being able to visualize the results in order to figure out whether the results are right or wrong. You can always look at the table of numbers, but looking always goes so far. That works when you have like 6 or 7 values. But then beyond that, it becomes difficult, and visualizing the result is really important. So let's learn how to plot. There is a module, you might realize by now, that for anything specialized, there is a special module that you need to import. Okay? And we're going to use so-called, this is the most common one for graphs. It's called matplotlib.pyplot. And that is quite a bit to type in. So we're going to typically give it a nickname, PLT. And that's some of the most common, this is one of the most common nicknames that is used for this. Okay? Now, before we start plotting, there's one thing we need to understand about computers in general. They're literal. So plotting things, they're not going to understand your function sign that you'd like to plot in terms of sort of a symbolic mathematical way. You have to precisely give it which points you want to plot. And if you maybe want to connect them with some surfaces and something really, it still has to, you have to give it all the points. So your first task in plotting anything is actually creating those points. And if I'm in a plane, then I need x and y coordinates typically of the points. Okay? So you have to have a precise set of however many points you want to plot. Even when things seemingly appear that they have infinite number of points, it's just appearance. It's not real. It's just that there's so many points that they appear continuously changing, okay, because of your eyes are not as good, okay, and the screen plots more points than your eyes can resolve, okay. So things are never super smooth and continuous. They're actually discrete on the bottom of it, and each point is plotted separately. Okay? So you always have to actually create those coordinates before plotting. Okay? So let's basically do a basic, so this is matplotlib. You can go to matplotlib.org, and there's all kinds of examples. Beware that like there's so many things that you could tailor in plotting that you will often resort to going to some online example that works and then modifying it for your purpose. That's perfectly fine. You need to know some very basic commands of how to plot things quickly, and then any kind of special plotting, don't be afraid of grabbing something from some online example that works. Okay? Just in general. So let's do a very basic graph. Open up Jupyter Notebook and let's plot a sine function. And I will do the same. There's my navigator. I'm going to open a new one. I'm going to navigate to my materials. I'm going to call this one Lecture 2.4 plotting. I have uploaded one version of it for you. Or BasicPlots rather. Okay. So kind of learn as a default just to type in import numpy as np. So this is the minimum of what you need to import. You could also just import the parent of this as matplotlib. I'm going to skip that for now. So first thing that I'm going to do is create points on sine, points for sine function that I'd like to plot. So I need my x and y values. Okay. Now my x values, this is where I'm going to create, I could type them in. We typically plot sine function between 0 and 2 pi, right? So I can use either linspace or a range. I'll let you pick which one you're going to use. I tend to default to linspace, but that's just my personal preference. And you can type in 2 pi is approximately 6.28, but pi is actually programmed in, and it's np.pi as a constant. So most of the common constants, e, pi, infinity, are available in NumPy, so np.pi will access it. So this is my limits are 0 to 2 pi. How many points do you want to plot? 30. Excellent. Let's plot 30. And then X is now my array, it's a NumPy array, and I can work with it. So I can actually execute the entire sign function using for every element in that array. And that I do by simply doing this. And this is great. I could have 30, I could have 3,000, I could have 3 million. My sign function will be evaluated for all of the elements of X. If you need to convince yourself that things are working as you wanted them to, then indeed you can plot the points. So first printed thing is your X, and then after that there is values, okay, of sign of X. I'm going to turn off printing now that I checked it out. And now I'm going to, I already imported matplotlot.plt as PLT. Let's just see what happens if I use, there's a plot command. And I'm just going to say plot X, Y. Nothing more complicated than that. Okay, looks like a sign function. So again, make sure to import what you need. Then make sure to create the points. And then after that, you plot them. And something has happened. Did you tell it to use blue color? Did you tell it to create this object, this graph with certain axes? No. So there are certain default decisions. It's going to kind of scope the values and just plot something for you. Okay? It has certain defaults that it works with, which is great because you can just quick and dirty plot just to see whether your points are there. Okay? And it appears continuous, right? Yes? Is it really? Can you see? Let's actually use less points. Let's go to something a little more drastic, like 8. Oh, okay, not as continuous anymore. So another default behavior is that, look at how I have corners. Those are my actual points, and there's 8 of those. And in between, it plots a line. Now again, if you have a lot of points, you will not be able to see that that line is actually straight in between, so it will appear continuous, okay? But again, it's plotting points, it's just connecting them in a certain way. So if I switch to 80, things are smooth, okay? And of course, the smoother they are, it's smoother with more points, except that at a certain point you don't see the difference, okay? I'm going to go back to 30. That's a good number. Now let's start adding things to this. So I don't want to just plot. I want to also modify. Okay? So one thing that I would like to modify is I can say, okay, how about red color? And let's go with circles. So now it will skip. It will exactly, the moment I start modifying, it's going to precisely listen to me. So I'm going to override the default. So now I just got a circle for every point and nothing in between. If you do want a line in between still, give it a command to give a line. So these things are additive. R is specifying a color, and it kind of knows, it kind of inspects what this R should stand for. 0 is a little circle, and line is connect things with line. And I'm not just coming up with these. It's not that you can type in anything and it's going to work. Okay? So there is an entire set of things. So for colors, there are certain pre-programmed colors, just for a very quick plotting. For line styles, there's more than just these. I'm plotting a selection. And then for partial list, for all of these is actually, and these are markers you could have. So there's a circle marker. It could be a plus, it could be an X, it could be hexagons, pentagons, squares, and so forth. Okay? So this you can play with however you'd like. Another thing that I'd like to do about this is label what it is that I'm plotting, okay? Now you can decide to do a title. Title is the entire, you will see the title appears here as a sine function. Last row, how is visibility? You can do. If I do a little bigger font, then not all of the text will be on the slide. So I gotta go back and forth. And then this is the actual result. I might want to label, and I'm not gonna do anything smart other than saying X. And then you will see that X shows up here. And I can also label Y. So X and Y are X label, Y label. If we had a Z, it would be a Z label. But those are 3D plots. So there's various ways I could do a title. I can also turn off the title, and I can actually label the actual line. But this label will not show up until I say PLT legend. So you can see that it's added as a legend. So BasicPlot is just plt.plot of xy, and all of the choices are made for me, which I might or might not like. And then we can kind of add things. We can dress it up. So I can do X label. Again, it's all in this family of commands. And you can see this PLT, this plot is sort of an object. So this X label, Y label will kind of get recorded, and then it's going to be plot once you actually plot the entire graph. So all of the specifications will kind of execute. Sometimes your Jupyter notebook might be a little cranky. You can also refresh, sort of like when you have too many things that you have specified and not all of them are showing up. Sometimes it helps to say plot show. Here at nothing, you will see no difference, but sometimes a good idea to refresh. So that all of the things you requested actually kind of cook together. Should I use that word? Again, I found it in my Jupyter notebooks sometimes, and I think that's a little bit of a communication between the actual Python and what is showing on the web page. I either have to execute this twice, just plot, shift, return twice, or Shift Enter, depending on which computer you are. But it's really optional. And nothing in your engineering decision actually works unless you compare it to something else. So let's actually plot two things on the same graph. I'm going to be very, very inventive here and use cosine function to compare. So I could just add x, y1 here. But I want to distinguish it from the previous one. So I'm going to say, okay, make this one blue and use little pluses. And label it, well, as cosine. So I just added one more set of data using the same x. It doesn't have to be the same x. And then I plotted both sine and cosine values, and let's compare them. And this legend should distinguish. Excellent, it does. And I did not request a line for my second set of points, so there's no line, that's fine. If you would like a line, add it. Well, let's do squares. Now, in terms of legend, you can see that actually this has switched location. It used to be here for sine, and then it jumped over here. So it's trying to optimize the location in order not to interfere with your data, which sometimes is possible, sometimes it's not. One final little thing, this graph is getting busy, which is possibly a terrible idea to pursue anything further. You can actually force text in a location. Okay? So here in a location, let's say 4.5, I have some space. Okay? So I'm going to drop text 4.5. So that's x and y coordinate of the location, and some string of a text. That's not, oops, no, it's not, it's in text. I'm talking and typing in parallel. Typically something goes wrong, okay? So this is in text, this is just dropping a piece of text and something, or I don't know, howdy. Let's see what happens. Whoa. And maybe closing the brackets. There we go. So you can see it started at 0.5 and started typing in. If I type something too long, it's going to interfere. So, you know, you tell it what to do. It's going to execute what you want it to do. Questions? Here's the, everybody got to do this? This is really the fundamentals of anything that you need to know. Now normally, just a moment, normally data comes from you and data is what differs in all of this things. One more thing that I possibly would like to do is to kind of show this. So this choice of axes seems to work just fine, okay? It's smart enough to figure out where to plot, but maybe you want a different choice here, okay, and here. Just be careful what you ask for, because it's going to execute precisely what you ask for. So I know that this is between PLT axis. So this is between, so obviously my x's are between 0 and 2 pi. And we know sine and cosine function are between minus and 1. So I can see that now the grid is way more tight and it's precisely within those limits. And that way it's always going to be plotted the same way, which might be important to you. But if not, just go with default. But default might execute slightly differently on my computer than on yours. Just beware, because there are different installations of Python. Okay, now I'm ready for a question. Yes?
Yeah, so two-part question. So the plots, you use two different lines for that. Is there, if you wanted to plot 10 different things on there, do you have to put 10 different plots, or can you?
You can concatenate, you can keep going.
Okay, and then the other question is that if you wanted to plot sine and cosine on two separate plots.
That's coming up. You're ahead of me. So let's just quickly, so I'm going to turn off, so I'm going to leave the axis as it is. And I'm going to turn off the legend here. But let's just do this, plot x, y, just to see what is the behavior if I try to do multiple. So I can actually, as long as I have pairs of data, I can say plot first one, then second one. And you can see that it actually did the choices for me in terms of color. I can still make all of these choices, just make sure to make all of the choices for the first pair after that first pair. And then all of the choices for the second pair after that second pair. And I can keep going. I can have 10 plots like that. So what I'm doing here, or rather it's programmed to accept different types of inputs. But it really just searches down the inputs and see what you gave it, and then decides how to act. You still have to be within the syntax. You can't just drop things in, okay? But it knows how to recognize and search for data versus what describes that data, the type of a plot that you'd like. That's called function overloading. So all of these functions can accept different types of inputs. So there's all these definitions on how you can call the function, but they all still have to be there. You can't just drop things because you feel like it, right? So there's still a syntax that is followed. Basically, in terms of fundamentals of the graphs, you can survive with what I've just told you. And you can make it as fancy as you'd like. Now I'm gonna actually copy all of this into a new one, which possibly I should have been doing, but this was quick to modify in place. And now I'm gonna do two separate plots. I'm gonna use this. I have an example, a different example on your slides if you'd like to play with the data, but I'm just going to compare sine and cosine, but with two different graphs, one above and below each other. So I have the data. And let's say that and I'm going to remove this text and PLT show. Okay. So let's simplify things a little. So I'm going to say PLT subplot, and I'm going to tell it, hey, there will be two plots, and the first one is 1, 1. And that first one will be the sine. And then I'm going to kind of repeat everything the same, except for the different, slightly different data in the second one. So this here, subplot function, indicates how many plots on one figure. So there's two of them, and then there's the position of the first one that you're going to add. And then everything you want to plot on that one, which is very similar to our previous figure. And then this is still same figure. I know that there's two of them, but the second one is in position 1, 2. And then X, Y, axis, legend, that's all the same, and I'm just plotting cosine. Let's see what it's going to do. So I'm going to give you a moment to type this in. Cut, copy, paste is your friend, and then modify after that. So everything in the second one is the same except for the subplot location, 1, 2 instead of 1, 1, and what I'm actually plotting, cosine. These specifications I left the same, or you could just have them nothing. You could just, these are all dress-ups, you can remove them for this particular purpose. And I ever so slightly reverted this, so I'm going to go back to the same order. Everything is the same, except data is different, and which subplot.
What is the one in the middle?
So 1, 1, 1, 2, so those are two different subplots location-wise, and there's a total of 2 of them, right? It's almost like a little vector.
Sorry.
1, 1, 1, 2.
What is the one? What is one?
So there's 2 plots. 1, 1 is the first of them. 1, 2 is the second of them. Okay. There could obviously be more, and there could be a 2 by 2 array, right? Woo. It's complaining. So sorry. In my quick haste, legend has to be after you actually identified that there is a legend. So initially, though. So label has to exist for legend to work. There we go. And you can see how it actually optimized the location of the legend into things. You might want to actually make your axis a little bigger to nicely accommodate these large squares. Okay? Everybody got this? All right. So I'm now going to combine, and I did not upload it before the class. I'm going to do it right now. I'm going to upload for you an exercise that you can download and execute yourself, or you can just watch what I'm doing. And I'm going to visualize matrix transformations for you. It's called 2.3, Visualize Matrix Transformations. So I'm going to create a square of points. And I'm just going to have about 8 points. Okay? There are corners of the square and middle of every square line. Okay? And I'm going to then transform those points. So at the beginning, when I introduced matrices, said that they actually denote all kinds of transformations that we could do with points in either 2 dimensions, 3 dimensions, or even more. But 2D is easier to see, so I'm going to work with 2D. And at the same time, I want you to think about any kind of movie artificial visualizations, those that actors didn't do, as well as video games, if you play video games, where you have to rotate the scene or do anything, catapult a person or an object to a different location, right? All of those, and actually to be plotted on the screen, all of those points and where they end up have to be given to the computer directly, verbatim, okay? So let's actually do that on a simple case, and next time you watch a movie, think about what it goes, like what kinds of matrix multiplications work in the background to actually get the movie effect that you're looking at. Okay, so first things first, I'm gonna import the packages here, as well as import numpy as np, which got somehow erased. Okay, and then I'm going to create locations of the points. So square points, there is 2 rows. These are x's and y's, and this would take a moment to just put a grid of square points on my paper. But basically there's a point -1, 1, -1, 0, -1, 1, -1, and 1, 0, and so forth, okay? Okay? So these are the points. And to plot these points, I'm going to do a scatter plot of the x locations and y locations. This is how I get them from the matrix if I'd like to. And I went, Ningyu suggested this marker, club suit. So you can do any kind of symbol. This is a latex symbol, club suit. And you have to give it an R to correctly execute. This is that formula here. So just, you can put a square here if you'd like, it doesn't really matter. Okay. And then I gave it a size of 500, and this you play with a little until you get the size that looks good, and color is R. So this is different ways to work with a scatter plot. Scatter plot is when I just have individual points that I don't want to connect with a line. So it's not your standard graph. And this I'm forcing the axis to not necessarily its size, but just to be square so it doesn't stretch in some weird way. Okay? And when you execute this first cell, which you can do on your computer, then you get, these are the points on my square. Okay? Now I'm going to manipulate them. First, I'm going to try to expand this square into a larger one. In matrix that does that, let's say that I want to go 2 times larger, is a diagonal matrix with 2 and 2 on diagonal. And if I make it 2 and 3, then x coordinate will go 2 times and y coordinate will be 3 times. So you can have weird stretches if you like. Okay? Like those weird mirrors that stretch you in a different way. So I'm going to expand, and this ratio is 2. And this is a matrix that is 2, 0, 0, 2, okay? And I'm going to print it. And then the way these 8 points that is defined, the way they actually go into there is just matrix multiplication with each individual column. But since I defined an entire matrix of them and each column is an individual point, it's going to work with all of them at the same time if I just multiply my stretching matrix, my expansion matrix, with this entire matrix of coordinates. Okay? So there is 8 of them. There could be 8,000. So my object on a computer could be much larger. Okay? But I'm just going to, and then I'm going to plot using this subplot. And I'm going to do a scatter plot, and I'm going to enlarge axis to actually see and make the axis the same in both of these subplots so I can compare. Are we following? Okay. So I'm going to just, this is my expanded square. It's just matrix multiplication, matmul, with this transformation matrix and my coordinates. Okay. And then I see where it goes by plotting using scatter. This is the matrix that does the stretching. Okay? These are my stretched coordinates. I can see that it's working well on these simple ones. And this is stretching twice. So my initial square is now stretched twice. Yes? That's pretty much it. Now I can play with that. In the next one, I'm going to shrink it twice. And I'm going to do everything the same. I'm just going to do axis smaller because I'm shrinking. So let's see what happens here. Oops, maybe I should have enlarged this axis a little bit because I cut off some of these fronts. But basically, there is my original and then shrunk. So shrinking is just matrix multiplication, diagonal matrix with 0.5 and 0.5. This is shrinking half, right? On diagonal. And when I multiply that with any coordinates, those coordinates get shrunk. And the way that I manipulate the entire object is to have all of the coordinates that belong to that object in one large matrix. Each column is my coordinate of a single point in that object. So even if it was me, okay, and I would have some sort of raster version of me, digitized version of me. Each point will be a little square. Okay? And then you would just do my matrix multiplication with all of the points describing me, and I would suddenly shrink or expand on the screen. So every time that procedure is done on a computer, that's what the computer does. Okay? We can do just simple translation, that's just adding a vector to something. So that's trivial. So that's just vector addition. So you can actually see how I can translate things. Whoops, and I got out of the frame. Okay, I need to adjust those. And then final thing that I could do is rotation. Well, that's not the only, but that's final example. I'm going to rotate things by 45 degrees. And in 2D, the matrix that does that is cosine of the angle minus sine of the angle in the first row, and then sine of the angle, and here I'm out of the sine and cosine in the second row. Okay, so cosine alpha, let's say minus sine alpha, and sine alpha, cosine alpha. When I multiply anything with that, I'm going to rotate in a positive direction, which is counterclockwise by that angle. Let's see what happens with this square. See, it's rotated. It could be any angle in between. Okay? So you can modify this in any way you'd like. You can modify this to 95 degrees and see what happens. Okay?